Okay, we're in Barnett's 12.1, and now we're going to focus on local extrema in the first derivative test. When the graph of a continuous function changes from rising to falling, a high point occurs, which we call a local maximum. Likewise, when the graph of a continuous function changes from falling to rising, a low point occurs. We call that a local minimum. Together, the two are called local extrema. We have a nice theorem in our textbook that says if f is continuous on an interval a to b, and c is a number in that interval, and f of c is a local extremum, then either f prime of c is 0 or f prime of c does not exist. That is, c is a critical point. If you take a look at this graph, here's an example of what we would call a local minimum, the point at c2. Why? Because we have a graph that's falling to the left of it, and then a graph that's rising to the right of it. Likewise, at c3, we have a local maximum. Why? Because our graph is rising and then starts falling past c3. Okay? Notice the point at c1 here. Our graph is falling to the left of c1 and then continues falling to the right of c1. So this is neither a local max nor a local min. This is nothing. It's neither. Likewise, take a look at what's happening at c5. The graph is rising from the left of c5 and also continues to rise to the right of c5. Once again, this is not a local min or max. At c4, we do have a local min, and at c6, we do have a local max. We have a rising graph and then a falling graph. Likewise, at c7, we don't have anything yet again, neither a max nor a min. Okay, so let's talk a little bit about the first derivative test. Make sure to read in full detail what's in the textbook about this. Let c be a critical value of f. That is, f of c is defined, and either f prime of c is 0 or f prime of c is undefined. Construct a sign chart for f prime close to and on either side of c. So in other words, we try to observe what happens to our function to the left of c and to the right of c. That's what we have in these two columns here. To the left of c and to the right of c. Based on our observations of the function, whether it's decreasing or increasing, we conclude if at c we have a local min or a local max, or, well, neither. So if the function is decreasing to the left of c and increasing to the right of c, we have a local min. Here's an example. I have some function that's decreasing to the left of, let's say this is my critical value, and then it's increasing to the right, so I have a local min. On the other hand, if my function is increasing to the left of c, and then starts decreasing to the right of it, then this is a local max. Alright, so that's another possibility. The third row of our chart talks about the function decreasing on both left and right of c. So if this is my point c, and my function is decreasing here, and then continues to decrease here, like this perhaps, then notice this is neither a local max nor a local min, because the function is decreasing on the left and decreasing on the right. Likewise, my function could be increasing from the left and increasing from the right, perhaps like this, of my function at c. Well, this is as well neither. It's not an extremum, right? Neither a local min nor a local max. That's what's illustrated in the last two rows of the chart. So, one other thing about the first derivative test, your textbook mentions in detail, f prime of c equals to 0 illustrates or indicates when c is in fact a local extrema, that we have a horizontal tangent line. So notice here's the two possibilities when it's a local min or a local max, the point, that the tangent line at c is always a horizontal line, right? This tangent line here is a horizontal line in both cases. So whenever the derivative is 0 and you have an extrema there at that point c, the horizontal tangent line could be drawn. Okay, so here's more possibilities. In here, you have to be careful. We have neither a local max nor a local min, and another situation where we have neither a local max nor a local min, but we still have the horizontal tangent line. Right? So again, the derivative could be 0, but it might be that you have neither a local max nor a local min. So be careful with those cases. Likewise, you might have a f prime of c not defined, but fc is defined. This happens at a corner or a cusp. So notice we have these corners, these cusps here, these sharp corners, and our function is defined in there, but the derivative is not. Regardless of that fact, there is still a local min and a local max at those points. So look at those carefully. Finally, f prime is not defined, but f of c is defined is another case. And in here, f of c is neither a local max nor a local min. Notice the derivative is not defined because if you think of it as the slope of the tangent line, well, the tangent line is vertical. And a vertical line has no slope. The slope is undefined. Therefore, the derivative here at the point is undefined. And we don't have either a local max nor a local min. Likewise, in this scenario here, same story. Okay, so you could use your calculators to use for the first derivative test. Rather, you could just do it on your graphing calculators if you have a TI-83 or 84 model. And I'm going to illustrate how to do that next. So if you go ahead and grab your calculator, the function we're going to be working with is f of x equals x cubed minus 12x plus 2. So there's two methods whenever you want to find possible local extrema. So the first method is to graph the derivative and then use the built-in function to find critical values using the zeros command under second and calc. So the first method is second and calc, and then we choose the zeros. Okay, this is when we graph the derivative. The second option is to graph the function, not the derivative but the function itself, and then use the max or min commands. So let's illustrate that for both. So here's our function x cubed minus 12x plus 2. On the right hand side with method 2, I've graphed f of x. So this is the graph of my function. Go ahead and grab this on your calculators. And to look for the maximum and minimums, we need to use those commands on the calculator. So let me bring that up. Okay, so my graphing calculator, I'm going to go to y equals. I'm going to get rid of anything else that's there. And the function that we want to graph is x cubed minus 12x plus 2. We're doing method 2 now. We're illustrating how to graph the function and use the max and min commands. So why don't we go ahead and graph this function. X cubed minus 12x plus 2. So here we go. X, to get to the cube, you could do math and option 3. And that will give you x cubed. Alright, minus 12x plus 2. Minus 12x plus 2. Alright, and let's do this in our standard window, zoom and option 6 for zoom standard. And as you could tell, the standard window will not be too good a fit because I'm escaping the peaks. Okay, I can't see the peaks on my screen, so why don't I zoom out, and I'm going to zoom out here at 0, 0, and then I'm going to see the peaks slightly better. So then what I want to do is I want to use second and calc, and then use the minimum and maximum commands, options 3 and 4. So let's find the local max first, 4. So we pick option 4. Then the calculator asks for a left bound. It wants us to go to the left of this peak point. So we use our left arrow key to get to any point to the left of it, and we hit enter to select it. Then we move to the right of that peak point to select the right bound. The calculator wants us to take a guess. You could just hit enter. And it's going to give us a maximum at x equals negative 2 of y equal to 18. So at x equal to negative 2, we get a maximum. At x equal to negative 2 right here. Okay, and notice the calculator puts a decimal. It puts a decimal there because that's the best approximation. I already have the minimum point here, but why don't we go through this calculation one more time. Second, calc, minimum, scroll to the left of this minimum point, hit enter, scroll to the right for a right bound, hit enter, take a guess, and we have a maximum of 2, 1.99998, pretty close to 2. Okay, so that's how you use your calculator for all of these methods, for this method, method 2. Why don't we illustrate the same thing, finding critical values now using the derivative of the graph. So you graph the derivative instead. Go to your calculator and graph the derivative, which is 3x squared minus 12. 3x squared minus 12, right? I'm getting this from here. Then, why don't we go ahead and graph this in the standard window. And it's a nice parabola. Here's what it looks like. Now, since this is the derivative, and the derivative is a polynomial, the critical numbers will occur at the zeros, where the derivative is 0. Remember, we don't worry about where it's undefined because it's a polynomial. It's defined everywhere. So what we want to do is figure out the zeros of the function. So we do second, calc, option 2 is 0. That's what you want, option 2 here. To get the 0, again, you have to scroll to the left of it, like I'm doing for this 0 here, hit enter to select that left bound, go to the right of the 0, right, anywhere to the right of this point here, and that's my right bound, take a guess, and you have that there is a 0 at x equal to 2. So that's how we get one of our critical numbers. Okay, 2. The other one, -2, is also found the same exact way. Let's do it really quick here. Oops, you do second in calc, 0, and you want to go to the left of your 0. There, I'm to the left of it. I'll scroll one more just so that I'm more to the left, and then get to the right of it. There is good, and the 0 is at -2. So that's how we get those two values. So in general, as theorem 3 in your book points out, if you have some polynomial f of x, and it's an n degree polynomial, then f has at most n x-intercepts and at most n minus 1 local extrema. So remember that that's a helpful theorem that's discussed in your text. In addition to providing information for hand-sketching graphs, the derivative is also an important tool for analyzing graphs and discussing the interplay between a function and its rate of change. So next we're going to take a look at some examples to illustrate this process in the context of an application to economics. So our next video will have some applications.